Hello, good people. It's me again. And so this is chapter 10, part 2 from Spatz. So before I talked about how to do paired and independent t-tests. So now we're going to talk and just talk about how to identify the independent and the paired and how to actually do those t-tests. Now we're going to talk about how to calculate effect sizes, confidence intervals, and talking about some power and what power means for the two-sample design. So this is the rest of part 10, or rest of chapter 10. All right, so let's talk about effect sizes. So we've been talking about effect sizes all semester. D, lowercase d, we talk about the effect between the difference between two means. Last exam, we talked about there's effect size indices for correlations. Lowercase r's are 1, 3, and 5, 0.1, 0.3, 0.5, whereas effect size indices for averages, for mean differences, are lowercase d's. So as you can see here, we've got for independent samples, we've got one effect size equation, and for paired samples, we've got a different effect size equation. The only difference, again, is this slight difference is this error term. So you see this fifth bullet point, I'll give you S hat or S hat sub D for you to calculate this kind of stuff, or it'll be part of the example that's already used. So that's going to be there, and what I need you to do is calculate effect size indices whenever you're doing t-tests. So if you're doing an independent sample, you take the difference between the two sample averages divided by the standard error, the standard S hat. For paired samples, you take the difference between each average, even though they're sort of from the same sort of groups because they're matched somehow, and then you got the S hat sub D. If you need it for your homework, go look it up in the back of the book. Don't take your time calculating it. As you can see, those calculations are pretty extensive, so just look it up in the back when you're doing your homework. What I really care about is making sure that you understand these things over here, the small, medium, large effect. Again, it's still 0.2, 0.5, 0.8. Anything between there, 0.3 is between a small and medium, 0.6 is between a medium and large, anything over an 8 is a large. There is no, when you're trying to write an interpretation, very large doesn't really mean anything. Like adjectives really don't really mean anything when it comes to, or adverbs, when you say very large, it's either large, small, or medium. That's kind of it. So I want you to memorize these 0.2, 0.5, 0.8s because, again, that's one of those things I want you to remember from this particular group, this class. And so the homework, or not the homework problem, but the worksheet problem from chapter 10 is creating a confidence interval around a mean difference. And so I talked about this in the worksheet, but here it is again. For independent samples, the lower limit, the upper limit, take the difference between the two averages. You subtract this numerical value. So what is this value? It's a t value, and you take the t and you multiply it by the error term. So again, as you see down here in this, what is this, the seventh bullet point, I'll give you these error terms. So you'll have these. What your job is to do is to look up the t value. And so in the worksheet, I showed you how to look up the t value. Again, you use that appendix C, table D. You look up that t value, and so you're like, well, how do I figure out that t value? It depends on what your confidence interval is going to be. So if you've got a 95% confidence interval, you have to use that column. If you're looking for a 99, if you're looking for 99.9, it just depends on what the question's asking about. Most of the time, SPSS and any researcher are looking for 95% confidence intervals. If you need to look up the error terms, if the question, the homework's asking you to calculate the error terms, don't do it. Just look it up in the back of the book. So that I really want you to focus all of your time figuring out how to find out what that t value is. And so, again, I talk about it in the worksheet video. You need a degree of freedom. So if you remember table D in the back of the book, you've got confidence intervals across the top, but then you've got to figure out what this t value is based off of degrees of freedom. And so I talk about in the video about the worksheet, but this, for now, independent samples is N1 plus N2. So N1 is the number of people in the first group, added to the number of people in the second group, and then you subtract 2 from it. That's your degrees of freedom. For a paired sample, it is the number of pairs that you have. So say you've got 25 pairs, you might have 50 people in your group, but they're paired, father, sons, mother, daughters, whatever. Then you got 25 pairs, you take 25, the number of pairs, and you subtract 1 from it. So that's how you get your degrees of freedom. So that's really what you need to be worried about in this particular slide, is if you're calculating these things, first and foremost, make sure you calculate them right. You're going to get these averages, just subtract them. You just got to find out where you're subtracting them from. So the first thing, the first main thing to understand from this particular slide is to figure out how to get the t-value. How do you get the t-value? Figure out, you got 95, 99, 99.9. So you know what column you're looking into, figure out what your degrees of freedom are, what I just told you. So that's one thing. The next thing is how do you interpret this? And so I talked about it in the worksheet as well, the worksheet video as well. How do you interpret this is based off of, you're trying to calculate with 95% confidence, with 99% confidence, how confident you are about the actual difference between those two groups lies between these two numbers. So let's just say the average Marian University shoe size is 9, but then you're like, all right, well, I want to get the average men's basketball team shoe size, and you're like, okay, so we do that, and let's say it's like a 15. So you get the average of a 9, but the men's basketball average shoe size is 15. So you got group 1, let's just say that's the average for all Marian, 9 minus 15. You got a difference of 6. What does that mean? So let's just say we calculate an upper and lower real confidence interval. We say that the real difference between the average college student and men's basketball teams lies between 9 and 4. And you're like, what does that mean between 9 and 4? That means the real mean difference, the real average difference. So if you're going to go across the United States and be like, all right, well, what is the average difference between the average college student and the average men's college basketball team? I'm 99% confident, I'm 95% confident that the real difference between those two groups lies between 4 shoe sizes and 9 shoe sizes. That's what that's saying. So obviously you really want to have a smaller confidence interval. Be like, all right, well, it'd be much better to be like, all right, well, if it's between 9 and 15, so it's a difference of 6, and my confidence interval is really between 5 and 7, you're like, ooh, okay, now I really have confidence about that. It's the average difference between these two groups is always going to be between a 5 and a 7. That's much better than saying, well, I know the difference is always going to be between 2 and 20. I'm like, well, that's not really all that helpful. So that's what that is saying. Two things you need to remember from this slide: how to calculate the t-value, how to interpret. That's how you interpret. These final two slides are a little bit more of like an exam theoretical kind of question. So making correct conclusions. Next chapters 11 and 13, next two chapters, 11 and 13, we're going to talk about assumptions and ANOVAs. And there's a lot of assumptions that are made when you're doing statistical analysis. And again, all you naysayers when it comes to research, and you'd be like, oh, everything's wrong, I could always poke holes in things. You're absolutely correct. You can poke holes in things. Doesn't mean we stop doing research. Just means you know what you're talking about. We make a lot of assumptions, and so we need to start talking about those assumptions so that you're aware of the assumptions that we use. So first and foremost, some of the things we assume in samples. So if you're taking 2 samples, let's just say we're taking the samples of all Marian University college students and all Marian University men's basketball players. We assume that those 2 subpopulations are normally distributed. What does that mean? That means there are more people that have the shoe size around the average of those 2 groups, and there's less people at the extremes within each of those samples. So what does that mean? That means for all Marian University students, I assume there's many fewer students that have a shoe size of 5, and there's fewer students that have a size 15, and there's a lot more that have a size around 9. And the same thing goes for the subpopulation for the basketball team. If the basketball team average is 15, there's very few men's basketball players that have size 9s, and there's very few that have size 20s, but there's a lot more that have around 15. So that's this idea that they're normally distributed within each population. variance are equal to the population. What does this mean? So the variation within these two samples are similar to all college students' variation, all men's basketball, collegiate men's basketball variation. So what does that mean? That means the Marian University student population, the variation within it is very similar to all college student shoe size variation. That's what we're talking about with variance equal to the population. And we controlled for extraneous variables. So I mean, when you're measuring shoe sizes, it's really not that big of a deal for extraneous variables. You're just using the appropriate measuring. You're consistent in measurement. You're not just asking them their shoe size, because there's some error associated with that. So there's some extraneous variables there. But if you're doing some drug research, say with Alzheimer's disease, there's a lot of extraneous variables that go into it. And we're talking about who are members, how good their caregivers are, what kind of mood they're in when they take these memory tests or these symptomatic tests, that kind of stuff. So there's a lot of extraneous variables associated with different types of research. So that's where we assume all other extraneous variables are controlled for. So the last video from chapter 10, the logic of null hypothesis testing, the logic of research is that you treat both of those groups the exact same way, except for one thing. And then when you find a statistical significant difference, you blame it on that one thing. Well, what happens if there's multiple things, multiple extraneous variables? What happens if one group was treated purposely different? Well, then you don't know the changes are due to the drug or this other extraneous variable. So we assume all the other extraneous variables are controlled for. That's a big assumption. The best way for us to assume that extraneous variables are controlled is this idea of random assignment. So what does that mean? Whoever gets into those groups is randomly assigned. So if there's variability, let's go down this really weird rabbit hole. So let's just say there is 10 weirdos, and I need 2 groups. Well, if I randomly assign all people to 2 groups, odds are going to be that I get 5 weirdos in one group versus the 5 weirdos in the other group. If I don't randomly assign, I have the possibility of having all 10 of those weirdos in one of those groups, and those 10 weirdos are going to affect my average for that one group. That's bad. So this idea is that, sure, weirdos could be weird in a lot of different ways, but if I put equal numbers of weirdos in each group, that weirdness actually averages out, and it's not going to have a huge effect on my overall average. So that's what this idea of random assignment tries to help with, that control for extraneous variables. So one extraneous variable might be like, ooh, I've got some weirdos. It's like, well, if I put equal numbers of weirdos in each group, then theoretically that weirdness will cancel each other out, and I'll still get a clean measure of what I'm talking about. So that's one of the biggest ways that we try to control for extraneous variables, is to have random assignment. All right, in this last bullet point, we use t-test to say we reject the null, assuming that is true. But what if the null is false? So what does this mean? Let's just say the null is false. The 2 averages are not the same, and you want to do some research. What does that mean? That means you sure as hell better find some evidence that the null is false, because it already is false. So you just stumbled on something that you should be publishing. So how do we make sure you don't stumble in the wrong directions? How do we make sure that you stumble in the correct decision if the null is false? Well, that's called statistical power. So statistical power is about making the possibility of making a correct decision when the null is false. So when you know that there's a difference between these things, you got to make sure you have statistical evidence to support that. So how do you do that? Well, if you look down here, the second bullet point, 3 factors that affect power. Number 1, effect size. How do you make sure that you find statistical evidence of a null false? You get a lot of people in your study, so you can't find a whole bunch of weirdos that don't display statistical evidence. So you got to find if the 2 averages are really different, the more people you get in your study, the more likely you're going to find those differences. The standard error of the difference. So what does this mean? You got to make sure that you put, like, random assignment helps with this. So if there's error, if there's a random pocket of error that's going to affect one group, you make sure that error is variable within each sample. So what does that mean? Effect size helps with that, but also so does sample size. And then finally, alpha. So like we talked about before, the type 1 versus type 2 error. if the null is false, you don't want to have type 2 error when you retain when you should be rejecting. So what does that mean? That means you can't have a crazy stringent alpha. So this is another reason why some people are okay with the 0.5, because that 0.5 is not too stringent. Statistical power is this probability of not making type 2 error. You want to make sure you reject when you should be rejecting. That's what type 2 error is when you don't reject when you should. So how do you make sure that you reject when you should? Get a bigger sample. That sample size is going to average out a lot of the error, and don't have so crazy of an too stringent of an alpha where you're like, no, I'm only going to use a p of less than 0.00001. Like, well, then you're gonna make some type 2 errors, that kind of stuff. So this is a broader concept. It's probably just going to be a couple questions on the exam and the final exam about power. What does this mean? You just want to have power. As I mentioned in class before, a buddy of mine wanted to know the bare minimum number of examples he needed in order to justify the effectiveness of some of his medical devices. Well, what he was asking for was like, what's the minimum amount of power I need? That's really what was going on here. And so he was asking me, we needed some bigger power. And so what do we need? We need bigger sample sizes. We need larger effect sizes. How do we get larger effect sizes? You make sure that you have smaller error within those groups. So what does that mean? You have more variability averaged out in those groups, and you don't set a too stringent of an alpha. So hopefully that's clear. There's also some discussion in your textbook about power, and hell, you can Google it. That'd be super fun. So that's confidence intervals, power, and what was the other one? Effect sizes for 2 sample tests. Stay tuned for chapters 11 and 13 when we get to ANOVAs. Thanks. Bye.